Good morning, our students, and welcome to this morning's class. Today, we have come again to discuss another very fundamental and foundational distribution in statistics called binomial distribution. Binomial distribution. Binomial distribution. Like we did in the previous class when we discussed Bernoulli distribution, we began first of all looking at the concept of distribution. So as a recap of that class we had on Bernoulli distribution, we ask ourselves, what is a distribution? In statistics and mathematics, a distribution is a mathematical function that describes all the possible values of a random variable and the associated probabilities within a given range. That is the definition we already had given while we were discussing Bernoulli distribution in our previous class. Any mathematical function that describes the possible values of a random variable, say x or y, with its associated probabilities within a given range is said to be a distribution. And like we already had said in that class, distributions are categorically classified into two, into what we call discrete distribution and continuous distribution. Into what we call discrete distribution, discrete distribution. Permit me to write this as a distribution and continuous distribution. Continuous distribution. We already had explained in that previous class that a distribution is said to be discrete if that mathematical function describes all the possible values of a random variable and is associated with probabilities for discrete outcomes. Discrete outcomes in the sense that the outcomes of that random variable are discrete and equally they are finite. Like I already had explained in that previous class, consider the toss of a coin. The possible outcome of the toss of a coin is either the head or the tail. Anything outside these two possible outcomes, it is no longer the trial of a toss of a coin. And then when this toss of a coin, the head is represented with 1, and then the tail represented with 0. You find out that the outcomes are discrete, number 1, and 2, they are finite. When you equally look at what we call the die has 6 faces. So discrete outcomes and equally finite outcomes. When such a random variable or when such a mathematical function describes the possible outcomes of such trials and the associated probabilities, we now say that that distribution is a discrete distribution. And in that class equally, we gave types of a discrete distribution. We gave types of what? Discrete distribution. Types of discrete distribution. Types of a discrete distribution. And then the first and the foremost that we enumerated that day is the Bernoulli distribution. Bernoulli distribution. And of course, we already had discussed the Bernoulli distribution in our previous class. So, situation whereby you are not very much okay with the knowledge of discrete distribution, please, we recommend that class for you because it was a detailed discussion on a Bernoulli distribution. The second one, of course, will lead to the topic of today, which is a binomial distribution. Binomial distribution. Binomial distribution. The other one is what we call the Poisson distribution. Poisson distribution. Another one is what we call geometric distribution of the first and second kind. Geometric distribution. Geometric distribution. In this geometric distribution, we are going to discuss its first and second kind. Its first and second kind. Second kind or kinds. Then we equally have what we call the hypergeometric distribution. The hypergeometric distribution. Hypergeometric distribution. These are some of the discrete distributions we have because the outcomes in any of the following distributions are discrete in nature and equally they are finite. Okay? Even if they are not finite because of what happens in Poisson distribution, we have what we call countable infinite. Understand? As long as it is countable. Okay? But today, what we have before us is what we call the binomial distribution. So we are going to wipe the board and begin our discussion with the binomial distribution. The next class is now going to be on the Poisson distribution. We continue till we exhaust the discrete distributions and enter into continuous distribution. Thank you very much and stay put as we want to begin our discussions on binomial distribution. When we discussed the Bernoulli distribution, we said that a random variable, say x or y, is said to follow a Bernoulli trial if that random variable x has only two possible outcomes, given as success and what and failure, with the probability of success given as what p and that of failure given as what as q. Then we say that such a random variable, such trial, is said to follow a Bernoulli trial. But then, when we now come to discuss about what binomial distribution, we say that binomial distribution, that a random variable, say x, is said to follow a binomial distribution if this random variable x is the sum of n independent Bernoulli trials. I will repeat. For instance, consider the following Bernoulli trials given as what? As x1, x1, comma, x2, comma, x3, comma, down to what? To xn. Each of these random variables follows a Bernoulli trial, such that this x1 has two possible outcomes, represented with a success and what and failure. And the probability of success in this x1 is the same thing with the probability of the success in what x2, down to what to xn. So this is a Bernoulli trial. It has two possible outcomes, success and failure. This is a Bernoulli trial. It has two possible outcomes, success and failure. Bernoulli trial, it has two possible outcomes, success and what failure, down to n trials of a Bernoulli experiment. Any random variable that is the sum of these independent and identical Bernoulli trials or experiments is said to follow a binomial distribution. What are we saying? That if I have what x, such that x becomes what x1 plus what x what 2 plus what x what 3 plus down to what to x what n. We now say that this x here is the sum of all these Bernoulli experiments or trials. And as such, this x here is said to follow a binomial distribution. So, the sum of independent and identical Bernoulli trial gives us what we call a binomial experiment or a binomial trial. That is to say, that I can say that this my x now follows a binomial distribution with parameters what n, comma what p. N here is talking about the number of what? Of a Bernoulli trials involved. And then the P here is the probability of what? Of success in each of these Bernoulli trials. That is to say that this P is going to be constant in all these Bernoulli experiments. That is the probability of what? Of success. It must have to be the same here, down to this particular place. So when this happens, we now say that X now follows a binomial distribution or a binomial trial. However, while we were discussing Bernoulli distribution in the previous class, we said that there is also another dimensional definition of these distributions. So I'm going to give another kind of a definition for binomial distribution that is actually going to help us now to factor in our mathematical function. Therefore, one can say that a random variable x is said to follow a binomial distribution with parameters what? P, n, and what? P. If and only if the probability mass function PMF of that random variable x can be written as, we have P of capital X is given as small what? X. Is given as what? N combination what? X. P of what? X. Q of n minus what? X. Such that X takes value from 0, 1 down to what? Down to what? To n. So any day, anywhere you see the PMF, probability mass function, which of course is that mathematical function that describes all the possible values of a random variable, what? X, with its associated what? Probabilities. And it is written in this format. You now see that this X follows what? A binomial distribution. And the range of a binomial distribution begins from what? From 0 down to what? Down to n. And this P here is the probability of what? Of success. And this Q here is the probability of what? Failure. Such that the probability of success P plus the probability of what? Failure Q must give me what? 1. Are we there? So if you want to evaluate the probability where this random variable X takes up a value what? A value 0. Then it means that when you come here, 0 goes in here, 0 goes in here, and 0 goes in here. And whatever thing that comes out here now is describing a situation where this random variable X takes up a value 0. Then when it becomes 1, 1 goes in here, 1 goes in here, down the what? Down the line. So anywhere you see the mathematical function given in this format, we now say that this random variable X follows a binomial distribution. And there is something I would want you to equally note. Remember that the sum of all the probabilities within the described range is equal to what? 1. Because probability doesn't go beyond 1 and it doesn't take up a negative value. And then we are talking about that this is a probability of a random variable x taking up a value what? A value x. Such that this value x, which is called the realization of this random variable now, begins from what? 0 down to what? Down to n. So this probability of this random variable x, taking all the possible values of this random variable, beginning from 0 to what? To 1, the sum of all of them must give me what? 1. That is to say, that if I say sum, are we there? Of P of capital X equals what? Small x. Such that what? X begins from 0 and ends at n. Is the same thing as sum of what? N combination what? X. P of what? Of x. Q of n minus what? X. Between the range of what? X running from 0 to what? To n must give me what? 1. So the sum of all these probabilities, this is 1 and this is 1. And of course you know that this is the same thing as this. Thank you very much. So permit me now to clean the board, because for now We have given ourselves the definition of what of a binomial distribution. We have equally given ourselves now what we call the distribution formula of or the distribution function of a binomial distribution given as this. So permit me to clean this now while we discuss what we call the moment of a binomial distribution in terms of its what mean or expected value and in terms of its variance. So permit me to equally clean this. Okay, let me read it. So we now talk about expected value of a binomial distribution. Expected value of a binomial distribution. Expected value of a binomial distribution. Expected value. Of course, when we talk about expected value of a binomial distribution, it is the same thing as saying the mean of a binomial distribution. So we can talk about what the mean of a binomial distribution means. So the question is, how is expected value of a random variable in the first place what defined? The expected value of a random variable in the first place is defined as, we define it as what? E of what? X is given as what? Sum over the range of x. P of capital what? X is given as small x. This is the definition of the expected value of any random variable x. Okay? But then when we now begin to make ourselves now to be looking at it as the expected value of either Bernoulli, expected value of either what? Binomial. Do remember that we just discussed the probability of a binomial distribution. So we now say but for binomial, we have that P of capital X equals small x is given as what? N combination x, P of what? Of x, Q of n minus what? X. For the range of what? X, beginning from what? 0 down to n. Beginning from 0, x what? Beginning from 0, 1 down to n. So the moment now we carry this and replace this, we should be talking about expected value of a binomial distribution and no longer expected value of any random variable x. It is now expected value of a random variable x that follows a binomial distribution, because I am now bringing in the PMF now of a binomial distribution to replace this probability of a random variable x. So I will now say therefore, E of what? X is now given as what? Sum over the range of x of this what? X. Then I'll now come here, it becomes what? N combination x, P of x, Q of n minus what? X. Such that what? X takes a value 0, 1 down to n. Okay? So we now move on. So we now say that this thing is the same thing as saying E of what? Of x is given as sum x takes a value from 0 to n to this what? N of this what? X. This my n combination x can be written as what? As n factorial all over. We have x what? Factorial into n minus what? X all factorial. Here becomes what? P of x, Q of n minus what? X. It can be written this way. Okay? My interest here now should be, how do I remove this x that is standing here all alone? That's my interest for now. I want to remove this x that's standing here all alone. So because this appears in factorial, this appears in factorial, this appears in factorial. So how do I now remove now this x that is standing all alone, not in what? In factorial? It's very simple. Look at what I do. This thing becomes what? E of x is given as, we have sum x is running from 0 to what? To n. Here I have my what? My x. This is my n. And this is n factorial. And this n factorial can be written as what? Multiplied by, we have n into what? N minus 1 all factorial. This and this are the same thing. I will say all over. Here is my x factorial. So equally, this my x factorial can be written as what? X into what? N minus what? 1 all factorial. Then I'll write what I have here, which is what? N minus what? X all factorial. Then I will now come here. We are going to pay attention here. This is p raised to power x. This p raised to power x can be written as what? P multiplied by, or let me put p raised to power 1 multiplied by p raised to power what? X minus 1. Then I'll write what I have here, which is what? Q of n minus what? X. Now, if you check p multiplied by p raised to power x minus 1, you find out that this p and this p, this common denominator. And in indices, when two expressions have common denominators now and you want to evaluate it now, you pick one of the denominators now and you sum the powers. Once you sum 1 plus x minus 1, you are left with x and you return here. So this and this, they mean the same thing. So it is on this note that we are going to do. Look at this x here and look at this x here all alone. So that you can cancel this x now and cancel this x. Let us try and bring outside everything that doesn't contain x and doesn't contain factorial. If you watch here now, n is standing all alone here. It doesn't contain x, it doesn't contain factorial. This p raised to power 1 is standing all alone, so I can bring them out. And I'll say, therefore, that my e of x now is given as, this n comes outside, we have n, this my p raised to power 1 comes outside. Then I will now have summation. Here I will now have what? This it becomes what? I have what? N minus 1 all factorial all over. Here becomes what? We have this is x for my dear, this is x. Because I said here is x factorial. So I have x into x minus 1. So I have x minus 1 all factorial into. Here becomes what? N minus what? X all factorial. Then I'll come here. What I have here is what? Q raised to power what? X minus 1. And then q raised to power what? N minus x. This is what I now have. At this point in time, I want to make definitions. Definitions could be, here I am seeing n minus 1, here I am seeing x minus 1. So I can say let t equals x minus 1. X minus what? 1. And if this t is equals x minus 1, it implies that t plus 1 is equals x. You can check it. If this t equals x minus 1, it implies that when this minus 1 comes over here, it takes plus, then it is equals what? X. I've made a definition. And I want to make another definition. And let s equals what? N minus 1. If s equals n minus 1, then it means I can easily return back here. Permit me, nothing is confusing much for now. So permit me now to clean the top because it's becoming a little bit, I need a space to continue the proof. But we began from here down to here. Just for any random variable x. We record for ourselves that for binomial distribution, this quantity is defined as this. Bringing this quantity now back into this place. We no longer call it expected value of any random variable x. We are now saying expected value of a random variable x that follows a binomial distribution. What we did here now was now to remember that n combination x can be expressed this way. N factorial into x factorial into n minus x all factorial, given as this. So what we now did here was, okay, fine, this x is standing all alone. How do I remove this x? I expanded this thing once, which is n into n minus 1 factorial. Because I expanded this in once, I must equally expand this x factorial once. Then I now came here and say x into x minus 1 factorial. This will help me to cancel this x and cancel this x. Then I came here, I had p raised to power x now. I can easily change it now to p raised to power 1 multiplied by p raised to power x minus 1. This quantity and this quantity are the same thing, like I had earlier explained. Now I'm trying to bring out everything from this expression that doesn't contain x nor factorials. I now have n p raised to power 1 sum of all these things. And I have made some definitions here. So permit me to clean the top now. Why will now put in this definition I have done into these things? So permit me to clean this. And even clean from binomial distribution. Okay? So I will now say therefore, my E of x is given as, here is my n, here is my p. Because anything raised to power 1 is that thing. So I just have to leave it at what? At p. So I now come over here. So here becomes what? Summation. Then remember that here is what? Okay, here is x is running from 0 to what? To n. And this time around, look at what our x here now. X is now t plus 1. So I will now come here and say t plus 1, running from 0 to what? To n. This is n minus 1, and n minus 1 is already s. So I can write what? S factorial. So I have s factorial all over. Here is what? X minus 1, and x minus 1 is already what? T. Okay? So I will now write what? T factorial. T factorial into. Here is my what? My n. So I will now put my what? My n minus. This thing is x, and my x is already t plus 1. So I'll open a bracket. Let me use this kind of bracket here. I'll open a bracket and write what? T plus 1. Close the bracket and close this one. Open this. Do it this way. So here am I at what? At what? P. So I have my P. This is x minus 1. And x minus 1 is what? T. So I have what? T. This is my Q raised to power n minus x. So I have what? Q raised to power n. Open a bracket. And then my x is already t plus 1. So I have what? T plus 1. I will close it. Okay? So what am I going to do further? What I'm going to do further becomes that is equals what? N P. Then I have what? Summation. This 1 and this 0, they are like them. So I can easily bring this one over here. If I bring this one over here, what I'm going to have is what? T equals minus 1 to what? To n. I have what? S or factorial all over what? T factorial. Then here I have, this is n minus t minus 1. So I have what we call, this is open a bracket, n minus what? T minus what? 1. That's what I have here. Then close the bracket. Here is p raised to power what? T, and then q raised to power what? N minus what? T minus what? 1. That's what I have there. Okay? So, permit me to equally clean here small. Clean this place more. Now, we are going to do something here very serious. We are going to do something here very serious. What we are going to do here very serious is this. The range which we defined earlier is the range that begins from 0. And what I have here is a range that begins from what? From minus 1. So what I'm going to do is now to find a way of how I'm going to remove this what? Minus what? 1. And if I must remove this minus 1 from begin from 0, I am going to add 1 here. And if I add anything here now, for me to balance the equation now, I must subtract from here. So what I'm now going to have here becomes that this equals what? N of P summation. That this my t now is beginning from 0. By that I have added 1 here to neutralize this minus 1. So here is going to be n minus 1. So I have my what? My s factorial into, here becomes what? T factorial into. You know that this thing can be rearranged like this. This thing can be written as what? N minus 1 minus what? T. This can be written that way. Then I have p raised to power what? T. Q raised to power what? N minus 1 minus what? T. That can be rearranged that way. And then what do I have now? This becomes what? N what? P. We have sum that t is running from 0 to n minus 1 of s factorial into, we have t what? Factorial into. Here becomes n minus 1 was already said to be s. So this becomes what? S minus. Here is what? T. S minus t all factorial. P raised to power what? T. Q raised to power. N minus 1 is what? S minus what? T. And of course, this thing can easily be written that this is n what p summation of t running from 0 to what n minus 1. Then we now have what we call s combination what t. Then we have p of what of t, q of s minus what t. And we said earlier that the sum of this probability is equal to what? 1. So if the whole of this is equal to 1, it means that what I'm going to have is what? NP multiplied by 1. We say therefore that our E of x is now given as what? NP. And this becomes what we call the expected value of a binomial distribution. Expected value of a binomial distribution. It ends this place. Okay? So what we are going to do in order to manage the size of this video is to take a question, a small question on this, then try as much as possible now that in our next video now we cover the variance and then a moment generating function of a binomial distribution. So we take a small question and then see how we can solve question on the binomial distribution and then be able to know exactly how to go about them. So please permit me to clean down. I don't think there's something too difficult. Let us take a question. That question says, and I read, it said the proportion of defective item in a manufacturing plant is 25%. Proportion of defective. Let me just write it what? P of what? D. Proportion of defective. They say it is given as what? 25%. They say in a random sample of 8 items, so our n equals 8. N equals what? 8. What is the probability that I, there will be no defective item. Number II, no more than one defective item. No more than one defective item. Then III, they say this is not more than, they say not less than 2 defective items. First of all, we need to establish if the question concerned is about binomial or about Bernoulli or about any kind of distribution before we begin to solve. Do remember that in Bernoulli, only 2 possible outcomes. Do equally remember that in binomial, only 2 possible outcomes. So let us establish whether it's talking about Bernoulli or whether it's talking about what? Binomial. From that manufacturing firm or plant, the items coming out from it can either be defective or non-defective. So it satisfies binomial, it satisfies what? Bernoulli. In terms of the items coming out either defective or either non-defective. How is it binomial? How is it Bernoulli? Or how is it binomial and not Bernoulli? In binomial, we are talking about the repetition of binary trials. And if you watch here, they say a random sample of 8 items. So the first draw that you made from that manufacturing plant or firm is Benoli. It's the one you have drawn can either be defective or non-defective. But the fact that you took another sample again, you are repeating the Benoli trial. And because of that repetition of a Benoli trial, it is now binomial trial or distribution. In fact, you repeated it up to 8 times, the number of trials there. If you flip the first coin up and it falls down, it's either a head or tail. This is Bernoulli trial or experiment. But the moment you pick and repeat again, you are now repeating different Bernoulli trials or Bernoulli trials, giving what we call binomial trials or experiments. Therefore, the question before us now is the question talking about the binomial distribution. And you and I already know that the probability mass function of a binomial distribution is given as what? P of capital X equals small x is given as what? N combination X. P of X, Q of N minus what? X, such that X takes a value 0, 1, dot to what? To N. Now, our interest here is on probability of a defective item, because that's what they mentioned, the defective item. That was why I wrote this as P of D. But I'm not just going to write now as P, where our P now is just talking about probability of defective item. They say probability of defective is what? 25%. So I will now come here and say, but. P, which is the probability of what? Of defective now, is given as 25%, which is 25 all over 100, which becomes what? 1 over what? Over 4. So the probability of defective item is what? Is 1 over 4. And remember that this Q is talking about now probability of non-defective. Probability of what? Of non-defective. So in that case now, what I'm now going to have now becomes what we call the probability of non-defective, which is now going to be what? Q. Probability of non-defective now, Q, is now going to be given as what? 1 minus 1 over what? 4. We are there. And then, of course, if you take LCM here, this is 1, then you'll be able to have, here is 4. 4 divided by 1 is what? 4. 4 times 1 is what? Is 4 minus. 4 divided by 4 is 1, which is what? 1. This becomes what? 3 over what? 4. So probability of defective is this. And probability of non-defective. Probability of defective is this. And probability of non-defective is what? Is 3 over 4. So, and in this case, like I've already said now, our interest now is talking about now on the probability of a non-defective. And then we are now saying that this RP now is talking about what? Probability of a defective, because that's where the interest is. So we now come over here, trying to solve the first one. There will be no defective item. So if you are talking about there will be no defective item, here is defective item, here is 0. Defective item here is 1, down to what? N. So if you are talking about there will be no defective item, you are saying that this random variable x takes a value of what? 0. Where 0 is talking about number of defective items. So in this case, you are saying this 0 is no defective what? Item. So in that case, what we are going to have becomes the probability of non-defective item now, P of capital X equals 0. Anywhere you see X here now, you replace with 0. So this is going to be, our N is already 8. So we have 8, combination what? 0, combination 0. My P here is 1 over 4. 1 over 4. So you are now going to have what? 1 over what? 4. All raised to power what? 0. All raised to power 0. We open it again. Our Q here is 3 over 4. So we have what? 3 all over what? 4. all raised to power what? 8 minus 0. 8 minus 0. So the moment you pick a calculator and evaluate this, you must have known the probability of a no defective item, where this random variable x takes up what? 0. Then when you say not more than 1, not more than 1, it means that you can have 0, you can have 1, but let it not go beyond what? 1. So in that case, you are talking about the probability that this random variable x is less than or equals to what? 1. That is not more than 1. And this thing includes probability that x is equal to 0 plus probability that x is equal to what? 1. That's what you are trying to say. Not more than 1. It can be 0, it can be 1, but let it not go beyond what? 1. So in that case, you are talking about probability of when x is 0 and probability of when x is equal to 1. We already have probability of when x equals to 0. So if I want to find this now, I will say therefore, my p of x less than or equals to 1 is given as, here is when it is 0, which is what? 8 combination 0, 1 over 4 all raised to power 0, 3 over what? 4 all raised to power what? 8 minus 0 plus. When it is now 1, it becomes what? 8 combination 1, open a bracket, 1 over 4 all raised to power 1 into, we have 3 over what? 4 all raised to power 8 minus 1. So once you evaluate this thing and then and sum them now, you must have gotten the probability. So it is not actually difficult. Then I'll quickly say something with respect to II. So saying something quickly with respect to II is that we are talking about not less than 2. Not less than what? 2. It cannot be less than what? 2. So there is no room for anything like 1. There is no room like anything like what? 0. Not less than 2. So it is from 2 above. So you are talking about probability that this random variable x is greater than or equals to what? 2. And this thing is the same thing like saying that this is 1 minus probability of x less than or equals to what? 1. They are the same thing. Because you are saying greater than or equals to 2, and you have the range. The range begins from 0, 1, 2, 3, down to what? To n. And you are saying not less than 2. It cannot be less than 2. It is from 2 above. So it is from this down to here. And we know that the sum of all the probabilities is what? Is 1. So the sum of all of them is what? Is 1. So if I should be talking about this one alone, I have to remove the probability of 0 and remove that of what? Of 1. That's why I have minus p of x less than or equals to 1, which is from 0 to what? To 1. So the moment you subtract it from there now, whatever thing that is left from this becomes the probability of when x is greater than or equal to what? 0. Thank you very much. Let us manage the size of this video and pause here and quickly go over to that of variance. And then from there, we now move over to what we call the characteristics function. Thank you very much for your audience.